Morning students, Elvis welcomes you all. Now we are ready with our new topic, and this topic is wave nature of matter or matter wave or de Broglie wave. Let me tell you what is the wave nature of a matter. Remember always the wave associated with a moving particle. The wave associated with a moving particle is called matter wave or de Broglie wave. The wave associated with the moving particle is called what? Matter wave or de Broglie wave. According to a French physicist, de Broglie, his full name is Louis de Broglie. Louis, Louis de Broglie. Louis de Broglie. According to him, he suggested that a wave can guide the motion of a particle. A wave can guide the motion of a particle. According to him, a wave can guide what? The motion of the particle. Louis de Broglie suggested that the particle like electrons, protons and neutrons can have also dual nature, that is wave nature as well as particle nature. That is, they have the dual nature like wave nature as well as the particle nature. And remember one thing, his assumption is based on the two facts only. That is, the universe is made up of particles and radiations. The universe is made up by particles and radiation. The universe is made up by particles and radiations. The very first assumption on the basis of which he has given that wave nature of matter, this one is what? The universe is made up by particles and radiation, and the second one is the most important one, the nature loves symmetry. So both particles and radiation must be symmetrical. The natures love symmetry. So the particles and radiation both have symmetry. These are the two assumptions on the basis of which he has given his view. And now just moving to the next topic, and this one is de Broglie relation. Always remember de Broglie, whenever you are writing, you just write D with a small letter and then Broglie like this. De Broglie relation. How will you find out the de Broglie relation? Let us talk about the energy of a photon is given by what? E is equal to h nu. This one is question number 1. But we know that the mass energy equation can be written like E is equal to mc square. So that by equating equation 1 and 2, we get what we get here, that is mc square is equal to h nu. Mc square is equal to what? H nu. Here we know that nu can be written like what? C by lambda. So we are just putting this value here, then mc square becomes hc by lambda. C cancelled out, then lambda is equal to h upon mc. This can be written like what? H upon p, linear momentum. And this wave is called de Broglie wave. And this wavelength is called what? De Broglie wavelength. Now if we are to find the de Broglie wavelength in terms of what? In terms of, we can say, the potential difference. So how will you find out the de Broglie wavelength in terms of potential difference? So for that, just remember one thing. How will you find out? We know that half mv square, the kinetic energy, can be given like ev. From here, mv square can be given like 2 ev. That can be written like what? M square v square would be equal to 2 mev. Here we are just multiplying both the sides with the m. Then what we are getting here, that is p square is equal to 2 mev. This can be written like p is equal to under root 2 mev. We can put this value here. Then we just get lambda is equal to h upon under root 2 mev. In terms of potential difference, if you are to get the wavelength, de Broglie wavelength, then it is written like h upon under root 2 mev. If we are just going to put all the values here for an electron, then what we get, look at here, if we are just putting the value h is equal to 6.6 into 10 power minus 34, m is equal to 9.1 into 10 power minus 31 kilogram, and E is equal to 1.6 into 10 power minus 19 coulomb. Then what we get here, what we get that what this unit can be given like joule second, I think. Okay, just what we get, that is lambda is equal to 12.27 upon root V angstrom. That is written like what? 12.27 upon under root V angstrom. I hope you have got this derivation of de Broglie wave, and this one is very important derivation. Very important derivation of this chapter. I hope you have got this derivation which has been written on the board. Once again, I am recalling this derivation. In this derivation, what we have read, that the energy of a photon is given by h nu. We have written that, and then we have written that mass energy equation is given like E is equal to mc square. Then we have only equated that equation, and we have got the value of de Broglie wavelength. Then we have just calculated the value in terms of what? Potential difference. Then we have put only the value. Then we have got what? 12.27 upon root V angstrom. I hope you have got this derivation. Thank you, as this will see you again next lecture. Students, now we are ready with our new chapter, and this chapter is dual nature of radiation. Let us start this chapter with the very first heading, that is electron emission. What do you mean by electron emission? Electron emission can be said as the ejection of electrons from the metallic surface, when an external energy source is given to that metal. What I'm saying that the ejection of electrons from a metallic surface, when an external source of energy is given to a metal, that is called electron emission. I'm saying that, I'm repeating my sentence again. That means the ejection of electrons from a metallic surface when an external source of energy is given to a system or the particular metal, that is called what? Electron emission. Electron emission can be understood on the basis of this, that every atom consists electrons, and the outermost shell of electron, or the electrons present in outermost shell, are loosely bound and moves freely inside the metal. Within the metal, they move freely. These electrons are known as free electrons. When an external source of energy is given to these particular electrons, they leave their orbit and move out. This type of ejection of electron can be said as what? Electron emission. What I'm saying, a metal consists number of atoms, and in that particular atom, number of electrons are present, as we know that. Chalo, Students, as this welcomes you all, now we are ready with our new topic of the chapter dual nature of radiation, and this one is work function. Let us talk about this. This is the minimum energy required. Electron from a metallic surface. The minimum energy required for the electron from a metallic surface is called what? Work function. The minimum energy required by the free electrons to just leave the metal surface, we can say that is called what? Work function. Or we can say that the minimum energy required to eject the electron from a metallic surface is called what? Work function. It is denoted by phi naught. And its value can be given like h nu naught. Here nu naught is like a threshold frequency. We'll talk about this later on. But before this, work function is measured in electron volt. And for this, we should know what is 1 electron volt. 1 electron volt can be written like 1.6 into 10 power minus 19 into 1 joule. That is written like 1.6 into 10 power minus 19 joule. So 1 electron volt is equal to 1.6 into 10 power minus 19 joule. So we have read what is work function. Work function is what? The minimum energy required by the electron to just leave the metal surface, that is called work function. It is denoted by phi naught, and its value can be h nu naught. We'll talk about this later on in the equation. Moving to the next, this one is threshold frequency. What is that? Threshold frequency. The minimum frequency the minimum frequency required to eject the electron from a metallic surface, that is called threshold frequency. The minimum frequency of light required to eject the electron from a metallic surface, that is called what? Threshold frequency. It can be denoted by nu naught. It can be denoted by nu naught. So we should remember this. Above this, only the electron can be emitted. Above this, only the electron can be emitted by the metallic surface. Below this, electron cannot be emitted. And if the value is just equal to the threshold frequency, then electron can be emitted. So the value of the threshold frequency should be greater. Or we can say that the frequency of the incident light should be greater than the threshold frequency, then only the electron emits from the metallic surface. So this is all about work function and threshold frequency. Now let us talk about photoelectric effect. The next one topic we are just going to study, that is photoelectric effect. Photoelectric effect. Let us talk about this effect. What is this? We have read the phenomena of emission of electrons, the phenomena of the emission of electrons from a photosensitive material or from a photosensitive metal or material. We can say that when a suitable frequency of light strikes on the metallic surface, then this type of particular phenomena can be set as photoelectric effect, and this type of emission of electron can be set as photoelectric emission, as we have read in the last video. So what is that? What is this one? This one is the phenomena of ejection of electrons from a photosensitive material when a suitable frequency of light strikes the photosensitive material. So this is about the photoelectric effect. Let us talk about the experimental setup of this. Experimental setup of photoelectric effect. Photoelectric effect. For this, evacuated tube is required, and there would be a window. From which a suitable frequency of light or a preferable wavelength of light can come. This window would have a lock of quartz which would allow only the suitable frequency of light to just enter in it. There would be two of the electrodes, one is set C and second one is set A. These two electrodes are connected with the battery. Two electrodes are connected with the battery as shown in the figure. As shown in the figure. What happens to the next? When the suitable frequency of light strikes that C plate, the ejection of electron takes place which move towards the A plate. That means this plate is a negatively charged plate and the electrons are moving from E plate to the A plate. So that the process continues itself, and electrons are emitted when UV radiations are made to fall on the photosensitive plate, that is C. These electrons get attracted towards the electrode A when it is at positive potential. That means we know that the direction of the electrons is opposite to the direction of the current. That is why I have changed this terminal. This terminal would be positive and this would be negative. If the electrons are passing from C plate to the A plate, then the terminal should be like this. So what happens to this? When a suitable frequency of light strikes the electrode C, then electrons emits, and these electrons are attracted by plate A. By this particular process, photoelectric effect occurs. I hope you have got this experimental setup also, and got all the topics which has been discussed here. As this will see you again next lecture. Thank you. Good morning students, as this welcomes you all. Now we are ready with our new topic, and this topic is laws of photoelectric emission. What are the laws of photoelectric emission? As we know that for photoelectric emission, the process in which a suitable frequency of light strikes or incident the metal or the photosensitive material, then the ejection of electron takes place. This process is called what? Photoelectric emission. So what are the laws of photoelectric emission? The very first law of photoelectric emission says that the minimum frequency required to eject the electron from metallic surface is called threshold frequency, and below threshold frequency no ejection of electron will take place. What is the first law? That is, below threshold frequency no ejection of electron will take place. What I am saying, the very first law says that the minimum frequency required to eject the electron from metallic surface is called threshold frequency, and below that frequency no emission of electron will take place. The very first law says about this, and the second law says this: the number of photoelectrons emitted per second, the number of photoelectrons emitted per second by a substance is directly proportional to the intensity of incident light. What I'm saying that the number of photoelectrons emitted per second would always be directly proportional to the intensity of incident light. And the third law says that the maximum kinetic energy of photoelectrons increases. The maximum kinetic energy of photoelectron increases with the increase in frequency of incident light. What I'm saying that the maximum kinetic energy of photoelectrons increases with the increase in what? Frequency of incident light. Now the last one is that the process of photoelectric emission is instantaneous. The process of photoelectric emission is what? Instantaneous. Let's recall these all four laws again. The very first law says that below threshold frequency no emission of electron takes place. What I'm saying, the very first law says that below threshold frequency there will no electron will be ejected from the metallic surface or the photosensitive material. So the second law says that the number of photoelectrons per second, the number of photoelectrons emitted per second by a substance is directly proportional to the intensity of incident light. And the third law says that the maximum kinetic energy of photoelectron increases with the increase in the number of the maximum kinetic energy of photoelectron increases with the increase in frequency of incident light. The fourth one is that the process of photoelectric emission is instantaneous. The process of photoelectric emission is instantaneous. This is all about what? Laws of photoelectric emission. I hope you have got all the laws, as this will see you in the next lecture. Thank you. Students, as this welcomes you all, now we are ready with our new topic, and this one is Hertz observation. I have made this particular setup of Hertz observation in 1887. In 1887, Heinrich Hertz performed an experiment to investigate. Heinrich Hertz has performed an experiment to investigate the production of electromagnetic radiation by means of spark discharge. He used a detector or a receiver. It is called what? Detector or receiver. He used a detector or receiver made of wire bent into a circle with the metallic space as it is shown S1 dash and S2 dash. As it is shown S1 dash and S2 dash on each end. A small gap was kept between these spheres. Electromagnetic radiation were produced with the help of induction coil. The electromagnetic radiation were produced with the help of induction coil, that is as it is attached with the system or the setup. Plates P1 and P2 and metallic sphere S1 and S2 dash. Plates P1 and P2 and S1 and S2 dash are attached with it. Then electromagnetic radiation falling on the detector induced a potential difference. Then the what? Electromagnetic radiation falling on the metallic sphere S1 dash or S2 dash induced what? Induced a potential difference. Induced a potential difference. This was evident as the sparks jumps across the gap. This is the evidence. What Hertz observed that this is the evidence of that spark. This was the evident as the sparks jumped across the what? Gap. Hertz observed that. What he observed? He observed that and the sparks across the gap S1 S2 jumped more readily when the detector was exposed to UV light. When this detector was exposed to UV light, then it was like more readily. It was performing the more readily, and it was getting the more resultant. The sensitivity of a spark gap device could be increased. The sensitivity of spark light could be increased with the illuminating it in the visible light, or we can say that we are just putting this to the UV light and we are exposing it to the UV light, then it can emit or it can detect the more light, or it can increase the sensitivity of the spark gap can be increased. So the conclusion that light can increase the emission of electrons from the metallic surface. That means what I'm saying? I'm saying that if UV light strikes of a suitable frequency, then that can increase the emission of electron. What is the resultant of this? I'm writing it here that light can increase the emission of electrons. So this was the resultant of Hertz observation. So I hope you have got this observation as Hertz observed. Now we'll be talking about what Healthwatch and Lenard observation in the next video. So I hope you have got this particular experiment. As this will see you again next lecture. Thank you. Morning students. As this welcomes you all, now we are ready with our new topic, and this one is Healthwatch and Lenard observation. According to this, what is this observation, Healthwatch and Lenard observation? What is about this? Let us talk about Wilhelm Healthwatch. The very first we will talk about the views of Wilhelm Healthwatch, then we will talk about the views of Philip Lenard. So let us talk about the views of Wilhelm Healthwatch. He observed that UV light thrown on a negatively charged zinc plate connected to a gold leaf electroscope, as it is shown. As it is shown here, electroscope decreases a divergence of gold leaf. This observation indicates the decrease in the negative charge on zinc plate. Thus, Healthwatch concluded that a negatively charged zinc plate, when exposed to UV light, a negatively charged zinc plate, when exposed to UV light, that emits the electron. What he said? He said that when a negatively charged zinc plate is exposed in UV light, that emits the electrons, and the emitted particles are in fact photoelectrons. And the emitted particles or the emitted electrons are in fact what? Photoelectrons. And now let us talk about the Philip Lenard. He said that when UV light was incident on a metallic electrode cathode, electric current varied in the circuit. This electric current in the circuit increased when UV light was incident on cathode. However, there was no current or lesser current in the circuit when the cathode was not exposed to UV light. That he concluded only light of suitable minimum frequency result in photoelectric current. This minimum frequency varies from metal to metal or material to material. The minimum frequency required to eject the electron from metallic surface, as we know that this is set at what? Threshold frequency. So he said that when these are exposed, he concluded that when a suitable minimum frequency strikes, then only the ejection of electrons takes place. And this minimum frequency varies from material to material. What is the conclusion of this observation, Healthwatch and Lenard observation? That is, the radiations of suitable frequency falling on a metallic sphere makes that surface emits electron, and the particular phenomena can be said as what? Photoelectric effect. This would be the phenomena of what? Photoelectric effect. I hope you have got this particular observation. Again, I am repeating the observation. According to what? Wilhelm Healthwatch in 1888, he observed that when UV light thrown on a negatively charged zinc plate emits a negatively charged particle when exposed in UV light. And now the Philip Lenard says that a metallic electrode, when the UV light was incident on a metallic electrode cathode, electric current varied in the circuit. This electric current in the circuit increased when only these are exposed in UV light. So that he concluded, what he concluded, a suitable minimum frequency results into photoelectric current. This minimum frequency varies from material to material. This was about what? Philip Lenard. So this is about all this observation. I hope you have got this observation. Thank you. As this will see you again next lecture. Thank you. Students, as this welcomes you all. Now we are ready with our new topic, and this topic is effect of intensity of incident light on the photoelectric current. We are just going to study what is the effect of intensity of incident light on photoelectric current. Let me tell you that intensity of incident light is always directly proportional to the photoelectric current. That means with the increase in intensity of incident light, the photoelectric current will also be increased, and that has been shown in this graph. These are the directly proportional. These have the relation of the directly proportional that is shown in this particular graph. That is IP is directly proportional to I. With the increase of IP, I would increase, or with the increase of I, IP would increase. And in the second graph, we have shown effect of frequency of incident light on the photoelectric current. Here, what we say, we observe that the intensity of incident light is kept constant, but the frequency of incident light is changed, so that in each case of nu1 and nu2, we have got the saturation current that is same. So saturation current does not depend on this. So now for a given frequency nu1 of the incident light, the positive potential at a plate A is decreased up to 0 as it is shown here. And it is found that the photoelectric current decreases. Now the plate A is given negative potential, which is increased till it becomes 0, and let this value is what? Let this value is V01. Let this value is what? V01. Then the experiment is repeated with the again new frequency, that is nu2, and it is found that it is at V02. It is up to V02. We are just experimenting, so that it is found that now stopping potential is higher than the V01. It is found that now the potential is higher than the V01. So what is the conclusion of this? Stopping potential is directly proportional to the frequency of incident light. Stopping potential is always directly proportional to the frequency of incident light, as it is shown, and the value of saturation current does not depend upon the frequency of incident light, as it is shown. So these are the conclusion of this topic. I hope you have got these two topics. Thank you. As this will see you again next lecture. Students, as this welcomes you all. Now we are ready with our new topic, and this is effect of potential difference on photoelectric current. What is the effect of potential difference on photoelectric current? Let us see here. I have made two of the graphs in which what I am showing, I'll tell you what I am showing here. In the very first, when light of suitable frequency, as we know that when light of suitable frequency falls on a photosensitive electrode, photoelectrons are emitted. These electrons are get attracted towards the electrode or plate, which is at potential with respect to electrode. They give rise to the electric current, and this current is called what? Photoelectric current, as we know that. When all the photoelectrons emitted by electrode reach to the plate, the photoelectric current has the maximum value. This maximum current is known as what? Saturation current, as it is shown here. This maximum current is known as what? Saturation current. Saturation current will not increase with the increase in positive potential further. The saturation current will not increase with the increase in positive potential further, as it is shown here. It will not increase with the increase in what? With the increase in positive potential. With the increase in positive potential. Now when potential of plate is decreased such that it attains a negative potential with respect to electrode, then photoelectron or photocurrent decreases. The minimum negative potential applied to the plate, for which photoelectric current becomes zero, 0, that is called what? Cutoff potential. That is called what? Cutoff potential or stopping potential. Remember these all points. And for this, the maximum kinetic energy half mv naught square a photoelectron must be equal to the energy acquired by an electron while passing through a potential difference. That means it would be equal to what? Half mv naught would be equal to what? ev naught. That means k max is always directly proportional to v naught. By the first graph we have shown here. By the first graph we have shown it here. And in the second one, the maximum kinetic energy of photoelectron can be determined by knowing the value of stopping potential. We know that. Now, if the intensity of incident light is increased and the frequency is kept constant, the values of photoelectric current and the saturation current are higher at high intensity of light than at low intensity of light. But stopping potential is same in both the cases. Stopping potential is same in both the cases as I2 is higher than I1 as it is shown, but the stopping potential V0 is same for the both of the cases. For both of the cases, what is the conclusion of this all? The conclusion is that saturation of photoelectric current depends upon the intensity of incident radiation provided frequency of incident radiation is greater than the threshold frequency. Because below the threshold frequency we know that there is no emission of photoelectrons. That is why it should be what? Greater than the threshold frequency. And the next conclusion can be like, for a given beam of incident radiation, the intensity of incident radiation does not affect stopping potential. That is, stopping potential does not depend upon the intensity of light. And the next conclusion can be, emitted electron may have different kinetic energies as it is shown here. The emitted electron may have different kinetic energies. Emitted electrons may have different kinetic energies. So I hope you have got these two graphs which are showing the effect of potential difference on photoelectric current and how they are affecting the photoelectric current. It is discussed in this video. I hope you have got all the points. Thank you. As this will see you again in next lecture. Good morning students, as this welcomes you all. Now we are ready with our new topic, and this one is graph for frequency and stopping potential. Let us see what is the graph of frequency and potential difference. Let me tell you one thing, that what? The threshold frequency depends upon the nature of substance. The threshold frequency depends upon the nature of substance. What the material you are using, that is also depend on that particular material. What I'm saying that the threshold frequency depends upon the nature of the substance or the material emitting the photoelectrons. And here the graph shows it is for two different metals, metal A and metal B. Here what we can see, the greater the work function, greater the threshold frequency. Greater the work function, greater the threshold frequency. The graph shows that there is a minimum value of frequency known as threshold frequency or cutoff potential. There is a minimum value of frequency which is known as what? Threshold frequency or cutoff frequency. Cutoff frequency of incident light, below which no photoelectrons can be emitted. And the graph for two different material A and B is shown here, in which we can say that the higher the work function, greater would be the what? Greater would be threshold frequency. Higher the work function, greater would be the threshold frequency. This graph shows like this. I hope you have got, according to this graph, you have just got all the points regarding this particular graph. Thank you, as this will see you again in next lecture. Morning students, as this welcomes you all. Now we are ready with our new topic, and this topic is Einstein photoelectric equation. This topic is what? Einstein photoelectric equation. According to Albert Einstein, when a photoelectron of h nu energy, when a photoelectron of h nu energy or when a photon of energy h nu falls on a metal surface, the energy of photon is used in two such ways. The very first, it is used, or the energy, a part of photon energy is used by an electron to just cross the what? Surface barrier, so that it can come out from a metal surface. What I'm saying, the very first, h nu is used in two such ways, that a part of photon energy is used. A part of photon energy is used to just cross by an electron to just cross the surface barrier so that it can come out from the metal surface. That is also known as work function. If you remember this, that is also known as work function. And the rest part is used to give the velocity. The rest part is used to give the velocity to the emitted photoelectrons, and this part of energy is always equal to the kinetic energy of photoelectrons, that is half mv square. So according to law of conservation of energy, we can write h nu is equal to half mv square plus fine. This one is like this. If suppose we are taking the kinetic energy of the system is 0, if suppose half mv square becomes 0, then if the kinetic energy of photoelectrons becomes 0, then nu becomes nu naught. We are just putting here that is h nu naught is equal to what? Phi naught. Now put this in this equation, then we are just getting h nu is equal to half mv square plus h nu naught. This can be written like half mv square is equal to h nu minus h nu naught, and this can be written like half mv square is equal to h nu minus nu naught. This one is known as Einstein photoelectric equation. This equation is known as Einstein photoelectric equation, and the kinetic energy of the graph of the kinetic energy to the frequency can be made like this, that the kinetic energy would show with the like this. We can, this one is nu naught and here frequency is being shown. So the graph between the kinetic energy and the frequency can be given like this. Now let us talk about the photons. What are the photons? Photons are the what? The packets of energy. These are also known as quanta. These are also known as quanta, and the quantum of energy ejected at the speed of light by an emitter. That these are also known as like that. And the energy of each photon can be given like h nu. Given like h nu. So these are the photons. If there is n number of photons, then E can be given like what? Nh nu. Nh nu. The energy would be given like what? Nh nu. I hope you have got these all. The very first we have read Einstein photoelectric equation. About the Einstein photoelectric equation we have read, when a suitable energy or when a photon of h nu energy falls on a metal surface. When a photon of h nu energy falls on a metal surface, this energy divides in two such parts, or this energy can be used in two such parts. The very first part, the energy is used to eject an electron to cross the surface barrier so that it can come out from the metallic surface. And the second one is that it gives the velocity to photoelectrons or to the electrons, and the energy of these electrons would be equal to the kinetic energy. And then we have just calculated, if half mv square becomes 0, then nu becomes nu naught, like threshold frequency, and then we have just put the value, and this equation we have got. This equation is called what? Einstein photoelectric equation. I suppose you just get all these points. And what are the properties of a photon? Let me discuss the properties of photon. A photon travels with the speed of light in vacuum. What I'm saying that a photon travels with the speed of light in vacuum. And the other property of photon is that rest mass of a photon is 0. Rest mass of photon is always 0. Remember these all properties. You all just remember these all properties of photons. And then the next is the kinetic energy of photon is what? H nu. Energy of photon can be represented like h nu or ht by lambda. Photons travel in a straight line always. Photons always travel in a straight line. Like that, we have just got all the properties of photons, and this is all about this video. I hope you have got all the points which have been discussed in the video. Thank you, as this will see you again next lecture.